We talked about the programmer's model being a set of registers that the user can read and write to. The user in this case was the programmer. So, what I want to spend this lecture is on the exact programmer's model of the M-class CPUs. So, we are going to look at the programmer's model for M-class CPUs. And so we talked about the fact that the CPU can be seen as, again, bunch of registers, and some of them we said were GPR, GPR, and some of them were status or configuration. Okay. So now what we're going to do is our intention is to kind of figure out what these and these registers are and what they mean. So we'll go back to this guide, the Cortex-M for Beginners guide, and kind of focus on this side of the diagram. Now, again, this is the programmer's model right here. It mentions it, and as you can see, there are just, registers being talked about. So all of these are essentially registers. Again, registers we said were a bunch of bits. It was some sort of a memory that could kind of, in this case for the programmer's model, represent the state of the CPU and provide us with ways to influence that state, right? Okay, so diving into what the programmer's model of the M-class CPU is, we would first want to kind of eliminate few things. So let's come back to this a bit later. This has to do with what all kind of modes in which the CPU can operate. We'll come to that in a bit, but we are going to right now for our current discussion ignore this. We'll also ignore this for the time being. Towards the end, I'll mention what this is kind of suggesting. And so with whatever is remaining on the screen, we will kind of just go ahead and make sense of that. So the M-class CPU um, is essentially can be thought of as 16 registers plus um, plus somewhere around like 5 special registers. So what's happening here is we in total somewhere have ballpark of 21 to kind of 24 registers, and I'll talk about why 24. Uh, but those kind of represent the state of the system, state of the CPU. And if we know what each of the registers mean, what bit in each register mean, we are pretty much done understanding the programmer's model of the M-class CPU. So the good news now is there are 16 registers that are called general registers, general purpose registers. So you can fiddle with those registers. And then of those, we have the last three here, R13, R14, and R15. By the way, each register has a name to it. So R0 through R15 are the general purpose registers, of which the last three registers, the R13, R14, and R15, are kind of special in terms of how they are used. And we'll come to that also. And then apart from that, we have these 5 registers, which is the status register, the program status register, whether or not the CPU is generating a negative number, did the calculation result in a 0 generation, so on and so forth, is kind of captured in the program status register. And then we have 3 registers here out of the 5 that relate to the interrupts, right? And then we have 1 register, which is the control register. So this register right here lets us configure something about the CPU, and the 3 registers here are giving us information and control on the interrupts. And then this one register here is providing status information about what the CPU is doing. And then we talked about the fact that out of the 16 general purpose register, R0 through R15, R15, R14, and R13 are kind of used for special purposes. We can also modify them. That's the whole point of calling them general purpose. But those three have a dedicated meaning to them. Okay, so let me then get an eraser and remove all of this. So we only want to focus on these registers right now, and we'll come to this in a bit. So let's go back to our diagram here. So then we mentioned that we have R0 through R15 as our general purpose register, meaning that the user can modify them. And then R13 is called the stack pointer. R14 is called the link register, and R15 is called the program counter. So they also have like a special name associated with them. And then in terms of the status and configuration register, we talked about the XPSR, which was the program status register. And like the details of this registers, we'll come to that also in a bit. And this is called the control register. And then there were three registers that kind of relate to interrupt status and a bit of configuration. So if we understood these registers, we pretty much have like a good handle on the M-class CPU. Now, in terms of whatever calculation the CPU does, that is kind of majorly taken care by R0 through R12. These 13 registers are used for that. R13 is the stack pointer, R14 is the link register, and R15 is the program counter. Now let's kind of take R15 and R14 out of our way. So whatever is the value of R15, that is exactly the location from where the instruction from the memory will be fetched. So if R15, the program counter was, let's say, hex 100 or 1000, then what it would mean is next time the CPU, like at the next clock cycle or the machine cycle, the CPU is going to attempt to fetch instruction from the memory location hex 1000. So the program counter kind of keeps on incrementing and pointing to the memory location from where the next instruction needs to be fetched. So that's kind of the role of program counter. Now the link register, uh, this has to do with the fact that CPUs kind of the code written for CPUs are of the nature where a lot of function calls are involved. We will kind of have snippet of code that calls another recipe or snippet of code that calls someone else, so on and so forth. So what happens is anytime you want to branch out to some other location to execute a recipe, when we return, we have to return to kind of the next instruction after the recipe. And so the question is that this address needs to be saved somewhere, and the link register helps in that. So let's say I have this function foo in C, which internally calls, let's say, bar, and then after that, I have this function baz. So when the program counter kind of goes and points to bar, the link register will save the address of the next instruction within foo, which happens to be, well, another jump, another branch to the function baz. All of this kind of becomes clear as we write assembly programs, but the idea is R14 is the link register used to remember where to go when a function call is complete, where to return to, what instruction to return to. So that's that. Now, R13 is the stack pointer, and the idea of stack pointer is that it's temporary storage that grows as function calls proceed. And so whatever is the number in R13, that is where the CPU assumes the stack to be. And when we do function calls or allocate local variables, the stack kind of grows. And then as we return from function calls or as we destroy the local variables, the stack shrinks. Now the interesting thing is M-class CPUs provide two types of stacks. One is called the MSP and one is called the PSP. So, and this kind of has to do with which mode and which privilege the CPU is operating in, which we haven't discussed yet. But the use of MSP and PSP is related to those. Now, R13 can either point to the MSP or point to the PSP. And that is exactly why here you see R13 mentioned twice, but R13 is just one register and it's either pointing to the value of MSP or it's pointing to the value of PSP. So PSP is like the process stack pointer and MSP is like the main stack pointer. And the idea here is sometimes it might happen that the application that you're running might actually exhaust the stack and then the CPU goes in a bad state. But when it goes in a bad state, it still needs to kind of kill your app or something of that nature. And the question is, when the CPU has to do that, some piece of code has to kind of go kill your app or manage it somehow, then that piece of code also needs a stack. And so the idea then is, if you have PSP that you have exhausted and that led to the CPU going in bad state and you're wanting to handle that bad state, then the code that is going to deal with that handling, that needs a stack also, and that is MSP. So it kind of has this meta reasoning behind it, and we'll come to that in a bit, but know that there is a reason to have two stack pointers, but at any point in time, the CPU can only point to one of those. And which one it points to, can we decide on that? Yes, absolutely. And that is exactly what the control register is for. One of the things that it is for. It controls which stack pointer is R13 pointing to, right? So that is that. Okay, so R0 through R12, general purpose register, user is free to use them in whichever way and form they like. It's just that R13, R14, and R15, they carry a special meaning for the CPU. The user can modify them as well, but modifying them will kind of influence or impact the state machine of the CPU, what it was trying to do, what memory location it was trying to fetch the code from, all of that can be influenced. All right, so then we can take a look at XPSR, the status register, and the control register. So let's go ahead and do that first. Again, we are yet to talk about this part. We'll come to that. Let's scroll down a little bit. And so here's an interesting bit. So this is talking about the control register and control register on various implementations of or the architectures of the M class of CPUs. And you'll notice that there are these two bits that are kind of common across all. And this 0th bit is kind of conveying, the mode and the privilege that our CPU is running in, and we'll come to the mode and the privilege. But the first bit here, the bit position 1, that dictates whether or not what stack we are using. Are we using MSP? Are we using PSP? That is dictated by this bit. Now there are a few extra bits depending on which architecture or microarchitecture this is the M class CPU belongs to that you're working with, and but pretty much these two bits kind of always stay. They're always available, right? One of them kind of uh, talks about privilege, and the other one talks about or gives us a control on which stack pointer to use. Okay, so that was the control register. Now we move on and talk about the XPSR register. Now recall, a while ago I had mentioned that the M-class CPU might have like 21 through 24 registers, 23, 24 registers. And the reason to that is we had like the 16 GPR plus the 5 control and status, and then XPSR among them. This register can split into 3. What does that mean? So we'll come to the splitting of 3 in a bit, but if we go up here, the control register, not control, the program status register, through its various bits, it's conveying the state of the CPU. So N, for example, is whether or not a negative number was generated. Z is for whether or not a 0 was generated. C is for carry. V, I think, is for overflow, and Q is for saturation. I think so. You can also, take a look at these on the internet. And then this T stands for whether it is thumb mode, thumb 2 mode, some few things about the instruction encoding. But then there is also, there are a few bits that talk about, execution state. And then there are these 9 bits here, 8 through 0, that talk about the exception number. So in our previous videos, we were talking about the NVIC conveying the interrupt number to the CPU. So the question is, how does our program get to know which interrupt we are supposed to attend to, or which interrupt has happened or occurred? And one of the ways to infer that is to look up these 9 bits. And depending, like if interrupt number 25 had occurred, then we see a number 25 here. All right. So now again, depending on which microarchitecture you're working on, the M-class CPU, you might have 5 bits or you might have 9 bits. And the M0 and M plus CPUs, they only support 32 interrupts or exceptions. Again, exception, will come to that in a separate video, but interrupt, you only have 32 of those, and hence you have 5 bits allocated to it. Now the idea is XPSR is kind of conveying status of the CPU, its execution state, and its exception related information. So there are 3 separate registers. You can call, they are kind of like shadow registers of the XPSR, and they are PSR, program status register. I think then one is EPR, I think, and one is EPSR, execution status register, something like that. And one is IPSR, which is interrupt related register. So this one kind of has only the first 9 bits. This has like the middle bits, and this has like these top bits. I forget exact names of these registers, but that will append to as like a note after the video. But that is essentially what the programmer's model of the M-class CPU is. We have a bunch of registers, they mean a certain thing, and the bits convey something, right? Now let's go back and talk about what these registers were. And in the next video, kind of will revisit what this is. Okay, so what is this? So if you're working with a CPU that is, let's say, M4, M7, M33, and so on and so forth, it's also written here. So what happens is these CPUs also have something called an FPU, a floating point unit. It's a piece of hardware that can do floating point arithmetic for us. And so sometimes if you're working with a CPU that has an FPU, then the FPU comes with its own set of registers for floating point operations. And then it also has like an SCR, which is floating point status and control register. So this is essentially available only if the FPU is available, and we need not worry about this essentially. We'll only kind of, focus on these. All right, so with this, we have pretty much covered the programmer's model for the M-class CPUs of different architecture types. And in the next one, we'll dive into the modes and privileges of the M-class CPU.